All right, so we're going to talk about quantum computing, and I'm hearing very good questions about quantum computing. Uh, Quantum computing is currently of no practical value, but the hardware is getting better fast, and the expectation is within 10 to 20 years, it will be able to crack public key encryption. And that means we all have to change our encryption routines now, because if you think about encrypting your data, it's not okay if it becomes decryptable in 10 or 20 years. Now, for some things like financial records, that might be okay because there's a statute of limitation of 7 years. But for a lot of things like your private data, your social security number, and your medical data, it's probably not okay if that becomes exposed even in 50 years, maybe even 100 years. So that's why everybody is now changing their encryption algorithms. And I think 4 or 5 algorithms have now been approved by the National Institute of Standards to be post-quantum encryption, which means encryption that cannot be broken even by a quantum computer, even when someone is developed. The current quantum computers are prototypes, and they are very noisy and very imperfect, so they cannot do very precise calculations yet. But they're improving all the time. And like I said, a prediction is probably in a couple of decades, they'll be able to do really serious things like crack, say, RSA encryption and elliptic curve encryption, on which the internet depends right now. So everyone is moving rapidly to the post-quantum encryptions, things like lattice encryption and learning with errors. And there's just a few of those ready to go. So let's talk about what quantum encryption is, what quantum computing is, rather. As you probably know, if you remember your ancient days of learning how digital computers work, all there really is like an XOR gate and a NOT gate in transistors. And you just put a lot of those together and you end up with a processor. The fundamental operations are you have digital signals coming in that are 0 and 1, and you can combine them to calculate XOR, or you can have one of them and flip it to NOT. And that's really all there is, just billions of those things stuck together. In quantum mechanics, the fundamental operations are completely different, which is why it can do certain problems much faster. So if you go down here, in normal computing, you only use the states 0 and 1. But in quantum computing, instead of using bits that are either 0 or 1, you use this thing called a qubit, which lives on this thing called the Bloch sphere. So you can have it in a state of certainty to be 0 or a state of certain to be 1, but you can also have a large number of intermediate states where it is somewhere between 0 and 1. And this turns out to be the way the world really is. And this is the part that I was mentioning before we started recording that hurt the brains of all the physicists I studied with, learned quantum mechanics. When you have like a tennis ball and you throw it, and then it goes and the other person hits it with a racket at the other end, the question is, if it passes through a dark zone where you can't look at it, where's the ball? And in Newtonian mechanics, you calculate a curve saying here's how the ball flies, and you know where the ball is at every instant. But in the real world, that is not what happens. When you throw an electron at a phosphorescent screen, you emit it from one location, and then it blurs out into a wave of uncertain location. And when it hits at the end, it only hits one spot. So things dissolve into like indeterminate ghostly states when you're not looking at them. But when you look at them, they collapse down to a single state. This sounds completely insane, but it is the way the world really works, and it actually makes sense. The question is, what made you think that you ever knew where something was when you're not looking at it? You have no reason to believe that. All you know is the result of experiments. When you measure something, things you are not measuring, you have no information about, and you have simply made the assumption that when they're not measuring them, they behave the same way they would if I was measuring them, and that turns out not to be true. And the most extreme example of that is the two-slit experiment, where you send something to two slits, and if you send one electron one at a time through a wall with two slits, it will create an interference pattern on the other side showing that every single electron dissolved into an uncertain state and passed through both slits and interfered with itself on the way to the other end. So this is the way the world really is. Real things are neither particles nor waves. They are waves when moving, and they collapse into particles when measured. That's how the world really is. And you don't really have any experiences that contradict that when you really think it through. The only thing you know is the result of experiments. You really don't know what was happening when you weren't looking. So anyway, that's the madness of quantum mechanics, and it's really true. So you make instead of having a digital bit that's either 0 or 1, you make one of these qubits, which typically involves having something like a magnet cooled down near absolute zero. So you can have one of these uncertain states and hold it. And you can operate on the thing in these uncertain states. And instead of just having actions like XOR and NOT, you have these things called gates that rotate it through different angles. So if you rotate it, say, 180 degrees about the x-axis, then it will change 0 to 1. But if it is in one of these uncertain states, that will rotate it to a different uncertain state down here. So you can operate on it with these gates. Now, for a while, IBM had a thing called Project Q, and they would let you control a real quantum computer over the internet, but they terminated that and changed it and limited it. So what we're going to do here is we're going to use a simulation of a quantum computer, a Python library. And for some reason, I couldn't get it to install on Google Colab or anything like that. Like I say, that's the problem with Python. Everything depends on versions of libraries and stuff. I found this place called Python Anywhere, gives you a free account that somehow has the right version of everything, so you can use this library. Um, Project Q. So now you can run it. So I've got a program here called q1.py. And so this imports the libraries, and then it just makes 10 qubits. It allocates a qubit and then measures it and then prints the result. So if you run that, it creates 10 qubits and then measures them. And the answer is it's always in state 0. When you create a new qubit, the library works by creating it in a certain state of 0. And I didn't do anything to change that. So when I measure it 10 times, it always comes out as 0. So that's fine. Now, let's take a look at the next one, which is Q2. Now I create a qubit in state 0. Then here I create it in state 1 because I'm going to create a qubit and then I'm going to run an X operator on it, which is that operator I described that rotates it 180 degrees about the X axis, and that will change a certain state of 0 to a certain state of 1. So now I've created the situation of digital computing. By the way, I should mention, in a digital computer, each bit contains only one bit of information, 0 or 1. But in quantum computing, this one qubit contains a whole lot more than one bit. It just depends on your precision. This is two floating point numbers, angles, theta and phi. So this could be 1,000,000 bits if you have a highly precise qubit. Now, as I said, our current hardware is not very precise, and therefore we can't really get a lot done with the current hardware of quantum computing, but they keep improving it. So the precision of your quantum computing is determined by how perfectly you can capture all these states and how perfectly you can cause them to interact with each other. So let's take a look at the third one. All right, and so now I create a superposition state. First, I make qubits in state 0 and see how they work. Then I make qubits and I rotate them with an H, which is a Hadamard gate, and a Hadamard gate only rotates it by 90 degrees about the x-axis, so it takes a certain state of 0 and turns it into an uncertain state that has a 50% chance of being 0 and a 50% chance of being a 1. So if I run that one, now you see this is in state 0. Here's the superposition state. So sometimes it's 0 and sometimes it's 1. And it's just a random flip, like a coin flip, to see which one you're going to get when you measure it. All right. And now we can do the most important thing, which is entanglement. Entanglement is a special thing you can do with qubits that you cannot do with bits. So let's look at that one. All right, now I create two qubits, qubit 1 and qubit 2. I rotate one to make it uncertain with a Hadamard gate, and now I entangle them with C0. So qubit 1 is connected to qubit 2. So qubit 2 was created in a state of certain 0, but then it was entangled with qubit 1 with this special property called entanglement, which is so important Einstein wrote a whole paper trying to disprove it, and it turned out he was wrong, and it's what really happens. So now they're pairs, Q1 and Q2, and now they're always identical. The first one should have been the first one's in a random state, either half zero or half one. The second one was created in a state of zero, but then entangled with the first one. This entanglement causes the two qubits to always be identical when measured. And so the second qubit inherited the uncertain state of the first one and will always give the same value when measured. It's not an uncorrelated uncertain state. It is 100% correlated with the first one. And therefore, these are the fundamental operations as opposed to XOR and NOT for bits. These fundamental operations make different mathematical operations possible and fast. And that turns out that they do make it possible to factor numbers into their component primes very fast. It's one of the many things that they can do. So you can make circuit diagrams. You have to make them as LaTeX files and then convert them to PDFs and such. But when you do, you get a nice little diagram like that there. This is the one I just talked about. You have two qubits. You rotate one with a Hadamard gate, and then you entangle them here. So now they're going to be tied. So this one becomes uncertain from the entanglement, not from the Hadamard gate. And you can make circuits with as many qubits as you like and set them up and draw pretty diagrams and see what patterns of things you get. And the main point of all this, I should point out, is Shor's. The reason anybody cares about this in the modern world is Shor's algorithm. And Shor's algorithm is there. Come on. All right. This particular pattern of inputs, you feed in a representation of a compound number, and it passes through all these entangled qubits, and out comes one of the factors. Just like you can blow white noise into a flute, and out comes as a pretty note because certain frequencies are constructively interfering in the flute and certain frequencies are destructively interfering. So it's a hardware device, like hardware computing, with these connections between the qubits. These qubits will be constructively interfering in such a way that you'll get an output that gives you one of the prime factors. So RSA encryption is shot. Even moving your RSA to 1,000,000 qubits will not save you. 1,000,000 bits long for the key won't save you if quantum computers actually work. So that's why anybody cares. And that's the first project here. We get to play with quantum computing just to see the basics of how it goes. And now you can see some stuff you can do with quantum computing. And I was very happy with this one. This is closely related to what I did for my PhD thesis. And so here's how it works. If I have a molecule like oxygen, O2 or H2, I start with two separate H atoms. When you move them closer together, the energy goes down, and then you push them too close together like a spring, they start repelling. So there is some equilibrium distance where they like to sit, where this bond is at its maximum strength. And so you can simulate this with a simulated quantum computing in Python. And so when you're done, you can calculate, you can initialize some qubits and prepare some variables, and you can then calculate the energy layout of this. This is the circuit that does it, in a simplified model of the input wave functions passing through various qubits and various transformations to measure it. And you can now calculate the minimum energy and get the energy surface, which looks like this. You can calculate the energy surface, and you can even calculate a hydrogen exchange reaction where you have an H2 here, and then you add energy until this hydrogen comes loose and goes over there. So you can get the energy surface for this whole thing, which looks like that there, of course. So you can have an H2 on this side or on that side, and that would be the same. And here's the energy required to rip one hydrogen out. So it lets you model the structure of molecules using both quantum computing and machine learning together. So I was pretty happy to see that. By the way, there's also protein folding, which is so easy. You can, in fact, run protein folding in a Google Colab notebook. It runs. I haven't written on the project for that. That's near and dear to my heart because that's also something I did for my PhD. Although at that time, my model was incredibly simple. I was actually a bone of contention when I was defending my PhD thesis because I modeled the protein as a clothespin, two sticks with one spring. And they said, this is an appalling model. You could have done that in 1730. Can't you do better than that? can't you solve Schrodinger's equation for all the atoms in the protein? And I said, no, we can't do that at all. Nobody can do it. And my advisor and other people backed me up, say, that's right. Right now, we're nowhere near being able to do that. But now they can do that with quantum computing, or with machine learning, rather. Machine learning can actually predict protein folding states, which I thought was centuries in the future. So some things, it's really showing spectacular results, just nothing that people will pay for yet. So the next one here, we talk about how curve fitting works, which is an introduction to where we're going, which is those Kolmogorov-Arnold networks. So to fit data, fit polynomials, this is something that's been around for a long time, although it hasn't been done with machine learning. But here you can fit a polynomial of degree 2 to this noisy parabolic data. But you could also fit a higher, if you had your degree is too low, you could put a straight line through it, and it will put the best straight line, but the straight line has systematic failures. All these are too high, these are too low, these are too high again, because it's not really a straight line. But you can also fit with a higher degree. The third degree fit still looks pretty good, but the ninth degree fit starts to do what I was telling you. This is what happened to Donald Trump. You fit too high a degree, and it starts fitting the noise in addition to the data, and so you'll get funny waving that shouldn't be there. And if you have fewer points, you get this sort of thing. All right, you can have a more complex curve, and you can use a polynomial of degree 15 to fit it. Remember, polynomials are kind of a questionable way to do this because every polynomial affects the whole curve. The line goes here, x to the 1, x to the 2, x to the 3. So every point, you got to include all those terms to predict every point. But that's how polynomials are fit. The alternative way to do it, which is what these Kolmogorov-Arnold networks do, is to use splines. So instead of fitting with polynomials, you fit with these spline things. The zero-order spline are just step functions that are 1 for limited range and then 0 elsewhere. The first-order splines just have a straight line going to a peak and then back down. Orders 2 and 3 start to look like a Gaussian, and that's what these splines are all localized. So now you fit the curve by adjusting as a parameter the weights of all these various splines, and therefore, if there's some part of the curve you don't like, you understand which parameters are controlling that part of the curve. Instead of hunting through a neural net and saying all these neurons could be contributing to it, you know that only a certain small subset of the weights affect the data in this area. So this should be more understandable, more interpretable, and more controllable than neural net models. And it may also be faster and better for some problems, although probably not all problems. And people are currently researching it. This is all very new, and people are trying to decide exactly what these machine learning models are good for. But they might be a big step forward. And that's what I wanted to show you, some of the sort of more advanced exotic things in the field of machine learning.